Good morning. Today we're going to talk about section 5.5, chapter 5, section 5, entitled Greatest Common Factor. Well, let's talk about the word factor. Well, as a verb, the verb to factor means to rewrite equivalently a sum of terms, where a term is a piece of a sum or difference, as a product of factors, where the word factors is a noun meaning an element of a product. So basically we're taking a sum of terms and rewriting it as a product of factors, hence the verb to factor, or the process of factoring. Well, I'm sure we all know how to factor something like 2x minus 4. You spot the greatest common factor of 2x and 4, and of course that's going to be 2. So I can really work my distributive law in reverse and claim equivalently 2x minus 4 can be written as 2 times x minus 2. Notice if I'm going in this direction, I'm factoring. And I can always check my answer in any factoring problem by multiplying. Factoring is really the reverse, or some say inverse, of multiplication. Right, so going from right to left, I'll call this multiplying. So in any case, 2x minus 4 is 2 times x minus 2. Again, the process is we spot the greatest common factor and work our distributive law really in reverse. Let's do something a little more substantive. Let's see, I'm going to give you a binomial of degree 6 and ask you to factor it. Well, right now at this point we've only got one type of factoring we're going to be talking about, and that is GCF factoring in this section. There will be other types of factoring later on in the text, as we'll see. Well, let's see. What's the GCF of 9x to the 4th y squared minus 12x cubed y cubed? Well, if I look at the coefficients first, 9 and 12, the GCF of 9 and 12 is 3, is it not? The greatest number that's a factor of both those numbers is 3. And I've got, well, let's see, I've got x to the 4th here and x cubed here, so that means I've got 3 powers of x that are common to each term of that binomial. And similarly, well, I've got a y squared here and y cubed here. I've got 2 factors of y that are common to both terms of that difference. Alright, so identify my GCF as 3x cubed y squared. So basically I can pull it out from that difference, working my distributive law in reverse. Alright, looking at the first monomial in this binomial difference, if I take out a 3x cubed y squared, what's going to be left? Well, I'm going to have a 3x, and that's it. What's left in the second slot? Well, if I start out with a 12x cubed y cubed and pull out a 3, what's left here is going to be a 4. I've taken out all the x's from this second slot, and I'll have one factor of y left. Alright, so I call this a GCF factoring. I identify the greatest common factor and work my distributive law to take out that factor from that polynomial sum. Okay? Let's try another one. Factor 4 a to the 4th b squared plus 6 a cubed b squared plus 2 a squared b. Alright, my first step here is to look for a GCF. And I'll consider the numbers first, the coefficients first. What's the greatest common factor of 4 and 6 and 2? Well, remember, greatest common factor is the greatest value that is a factor of each, and certainly 2 is going to be the GCF of those coefficients. Similarly, what's the greatest number of powers of a we've got in all of these terms in this polynomial that's common to all? And of course it's going to be an a squared is common to all. And how many powers of b are common to all? Well, only one b is common to all 3 terms. So I can factor out a 2a squared b. What's left inside? Well, I'll get a 2a squared b in my first slot plus 3ab in my second slot plus, now notice I've taken everything out from this slot, 2a squared b, so I've got to leave what I call an invisible 1 left as a factor. Now you can always check your answer by multiplying in this type of factoring problem. Alright, and certainly I can see that 2a squared b times 2a squared b is going to be 4a to the 4th b squared. 2a squared b times 3ab will give me a 6a cubed b, and 2ab a squared b times positive 1 will give me this last term here. So it does check out by multiplication. I don't ask you to formally check each and every one of these factoring problems, but certainly if you're stuck or wonder if you've got a correct answer, you could check your answer in those situations, in those more difficult situations. Let's factor this. 9x plus 16. Well, I stare at this for a while and I realize 9 and 16 are what they call relatively prime. They contain no common factors except for a 1 or possibly a negative 1. So I can't really meaningfully factor out anything from those coefficients. And x, the x variable, is not common to both terms. Alright, so when you can't factor anything out from a polynomial expression, I call it prime. No meaningful GCF here, a prime polynomial. Just like prime numbers can't be broken down into products of other integers, prime polynomials can't be broken down into products of other polynomials. Alright, our author makes a big deal about this next technique. Factor a minus 1 from this trinomial of degree 4. Alright, the reason we do that, as we'll see in later sections in this chapter, it almost always behooves you to set things up so you've got a lead coefficient that's positive, and I can always factor out a negative 1 from any expression just by changing the sign of all the terms it contains. So I claim this equals this expression here with a negative 1 factored on the outside. Okay? And we usually don't write 1, it's kind of redundant, so we could, I think our author would give this answer in this fashion. Your answer would be negative parentheses b to the 4th plus 3b squared minus 2. Alright, try another one. Factor. Well, at this point, factor means find a GCF factor, and here in this particular problem, we're going to say factor a negative 1 from 5 minus x squared. Well, remember, when you're factoring a negative 1 from any polynomial, well, essentially you change the sign of each term of the polynomial it contains and set a minus 1 outside a pair of parentheses. Alright, so I can factor a negative 1 out from any polynomial expression I like, basically by changing the signs of all the terms it contains. I think our author would probably put the answer like this, leaving that parentheses expression, getting that in standard form. And again, maybe it's redundant to show a factor of 1. Alright, we could give a final answer of negative parentheses x squared minus 5. Alright, Book's got a bunch of these type of problems. Factor, well, let's see. He words it like this: factor the opposite. I'll put that in quotes because that means seem kind of vague. Factor the opposite GCF from this expression here, minus 6 u squared v cubed plus 8 u cubed v squared. Alright, when they say factor the opposite GCF, they're really saying they want the GCF to be a negative. Alright, if I look at these coefficients, let's see, the GCF of 6 and 8, I suppose I could call that a 2, but again, they want this is the implication here, they want that GCF to be negative, so I'm going to arrange my signs, not to factor out a 2, but to factor out a negative 2. Alright, how many powers of u are common to both terms? Well, 2 factors of u are common to both. And similarly, v cubed, v squared, I've got 2 powers of v common to both. So my GCF, I claim, is going to be minus 2 u squared v squared times the polynomial that remains within. Well, if I take out a minus 2u squared v squared from the first term of this binomial, I claim I've got a 3v left. And you could kind of check your answer. Minus 2 times 3 is minus 6. U squared, well, there is no other u here, so I have a u squared in my original term. And v squared times v is, of course, v cubed. So that first product does check out. What's next? Well, I'll need a minus here. Minus 4. Minus 2 times minus 4 should be positive 8. Recall, u squared, I'll have 1 factor of u left here, and I've taken out 2 factors of v, so no factors of v left inside. So my final answer is going to be 3v minus 4u. So minus 2 u squared v squared times 3v minus 4u. Factoring GCFs. Alright. Factor. And don't panic, this one's got fractions in it. It's still a polynomial. We can still do a GCF factoring here. Alright, so I've got a trinomial of degree 5 and 2 variables, all with fractional coefficients. Well, your first step in these GCF factorings is to find the GCF. And I think you can see all these fractions are multiples of 1/5. So I'm going to factor out a 1/5 from all those coefficients. And let's see. How many powers of a are common to all? Well, this middle term doesn't have any a's in it, so I can't factor out something that's not common, so I can't factor out an a. How many powers of x are common to all terms? Here I've got an x to the 4th, an x squared, an x cubed. I think I can factor out an x squared according to my distributive law. So you've got at least 2 powers of x in each of these terms. Alright, so I claim this expression then equals, well, 1/5 x squared is going to come out. What stays inside? Well, I'll have an a, or I should say 3a x squared here in the first slot, plus, well, if I take out 1/5 x squared from 1/5 bx squared, all that's left is a lonely b. And then minus, well, if I take out a 1/5 x squared, I'll be left with a minus 4 a x. Final answer, 1/5 x squared times 3ax squared plus b minus 4ax. Alright, we'll call it a day for section 5.5, greatest common factoring. And that is all.